Now remember, the free mass spring system was given by this initial value problem where we had a mass that was in a damped medium and is providing a damping force that prevents the motion of the spring. Any motion that happens in this particular case is due purely to the initial conditions, the initial position and the initial velocity. So you could imagine that if you held the spring below its equilibrium position and you let it go, it would start to bounce back and forth. So in this situation, there are 4 cases of motion. Now, I say 4, but one of them is not realistic. The undamped case is an idealization. In the real world, no matter where we are always going to have some sort of damping due to the medium we're in. So realistically, the next 3 cases are those that occur. Now, what's important here is that these are all transient motions. And what I mean by that is that if you let time run, all of these in the realistic cases are going to go to 0 as time goes to infinity. Now, there is one special case just worth mentioning, right? And this is the case of rest initial conditions. So if this value y0 is 0 and the initial velocity v0 is 0, then by uniqueness, you should be able to see that y equals 0 solves the problem, and it has to be the only one because it is the unique solution. What we want to do today is study a driven mass spring system. Schematically, or in terms of a little picture, you could imagine this spring mass system is hanging from a ceiling or some apparatus that is moving. And so we say that this is providing a driving force. Now, mathematically, the system that we're going to talk about here is the same second-order differential equation, except we are going to drive it by some force that's sinusoidal. Now, it could be a cosine, it could be a sine. It isn't really important. Remember, one is just a shift of the other. But what's important here is that there is a periodic driving force. What happens in a situation like this? If I have a periodic driving force, what type of behavior should I expect? So it really depends on the frequency of the driving force. The main feature that we really want to try to study is something called resonance. Now, resonance is where the driving force is very closely tuned in to the natural vibration or oscillation frequency of the system. You can see this for yourself when you're on a swing. I posted a link to another video that has an experimental setup of a mass spring and somebody's driving it, and you can see the resonance behavior where using the same strength of driving causes these wildly strong oscillations, very, very high amplitude. That's the characteristic feature. Can we model this behavior with our initial value problem? I'm going to study a special case first, just to try to show you that even the simple model that we've got has the potential of doing this. So we're going to study a special unrealistic case first. This is going to be an undamped driven system. We'll talk about an undamped case, and in undamped case there is no y prime term. So we've just got this my double prime plus ky equals 0. And I'm also going to take rest initial conditions. So I'm going to talk about putting everything starting from rest. And rather than having a right-hand side that's 0, because then nothing would happen, I'm going to start by taking some right-hand side with a certain frequency. I won't call it 0. I'll just call it omega t. Okay, now we know that the solution has to be comprised of a homogeneous portion and a particular portion. So the homogeneous portion is easy to figure out. My double prime plus ky equals 0. We know that y is going to be some e to the lambda t. This is going to take us to the following simple equation. Lambda will be plus or minus the square root of k over m I. And we're going to call this omega naught. Omega naught will be the natural frequency of the system. The homogeneous solutions, as we know, are going to be some C1 cos omega naught t plus some C2 sine omega naught t. We can do a little bit of work and write this as some sort of cosine omega naught t with a phase shift. Let's model the particular solution with a complex exponential, EA times some e to the I omega t, and we'll note that our right-hand side is just the real part of some f naught e to the I omega t. So what we're going to do is use this complex exponential as our particular solution, and then we will take the real part of the answer once we get it, because the driving force is the real part. Yp is a e to the I omega t. We need the derivative, so that'll be I omega a e to the I omega t, and yp double prime is going to be negative omega squared a e to the I omega t. Remember, when you've got two factors of I multiplying together, they multiply to give you a negative 1. So we're going to sub this into our differential equation, and we'll have m times y prime, so I omega t plus ky I omega t is going to be equal to our f naught e to the I omega t. So remember, we're trying to figure out what the value of a is that will satisfy this differential equation. So we can reorganize everything. We'll have an a e to the I omega t, k minus m omega squared equals f naught e to the I omega t. So these e to the I omega t's can just cancel out. You should be able to find that a is f naught k minus m omega squared. Now note, all of these constants are real, right? They're real valued. So that means your particular solution will just be f naught k minus m omega squared e to the I omega t. Now we are going to extract the real part of this. This cosine can be, this e to the I omega t can be written as cos omega t plus I sine omega t. And that means that the real part will give us our particular solution, f naught k minus m omega squared cos omega t. Omega naught squared is really k over m, and so that means that k is m omega naught squared. So the particular solution in this case is going to be f naught m omega naught squared minus omega squared cosine omega t. Now, the full solution is going to be given by our C1 cos omega naught t plus our C2 sine omega naught t plus this particular solution that kind of looks like this with some squares in the bottom. So I'm going to skip the details and I'm going to say we're going to apply the initial conditions. We will find that C2 is 0. We'll find that C1 is negative f naught m omega naught squared minus omega squared. So when we put this all together, the full solution here has one amplitude out front, just like that. And then we have this difference here, cosine omega t, cosine omega naught t. Is what is the behavior of this thing? What does it do? What happens as I get closer to some special frequency, the natural frequency? So the cases we need to talk about are when omega naught is not the same as omega. So when you're driving it at a different frequency than the natural frequency. I'm not going to get into this right now, but there's a phenomenon here that's called beats. And that can also be modeled here, but that's not what we're interested in. What we are interested in is what happens as the driving frequency gets closer to the natural frequency. So what we're going to do is take a limit as this omega gets closer to omega naught. So in the limit that omega goes to omega naught, we're going to take the limit of this expression, our function. What did it do? Now, this is going to be an exercise in calculus. And in particular, if we were to take a look at this limit, you see that as omega gets closer to omega naught, upstairs the cosines will approach 0, and downstairs these omega naught terms will also approach 0. So what we're going to do is use L'Hopital's rule. The limit as omega gets closer to omega naught, we're going to take a derivative with respect to omega of these two terms. Remember, omega is the variable here, divided by the difference, or sorry, the derivative of this difference. And so the derivative of cosine is going to be sine, so we'll have a sine of omega t. Now remember, we're taking an omega derivative, so we'll get a negative from the derivative there and another factor of t. That's really important. Downstairs, we'll get a negative 2m omega. Sine omega t, 2m omega. Now, as that approaches the natural frequency, there is no longer any problem as far as the limit being indeterminate. So we get this. So as omega goes to omega naught, the particular solution then becomes the following. It becomes this f naught over 2m omega naught with a t in the front, sine omega naught t. This is something called pure resonance. And it's pure because it comes from the undamped case. And if we were to plot the behavior of this thing, and it shouldn't be yp, it should just be y. If we were to plot the behavior of this thing, what would we see? We would see, starting from rest initial conditions, we would see some oscillations. And as time went on, the magnitude of those oscillations becomes unbounded. And it has this linear envelope on the front. When you drive your system at its natural frequency, you get a maximum response in the amplitude, in the energy that you provide. Now, this is non-physical. It's non-physical for two reasons, right? Number one, there was no damping. And number two, we have unbounded oscillations as t goes to infinity. In real life, you cannot have infinitely large amplitude. And so, this was a first simple check on, can our basic model exhibit something like resonance? It can. But now, can it exhibit that sort of behavior when we have damping?